that better? Yeah. Okay, excellent. Good afternoon. My name is Madden-Rusnak. I'm a developmental psychology PhD student at the University of Texas at Austin. And the title of my talk today, just like Kai described, is Testing Porges' Polyvagal Theory, Evidence for Real-Time RSA Changes with Natural Infant Stress. So Porges' polyvagal theory posits that we can complete rapid shifts between our rest and digest parasympathetic nervous system and our fight or flight sympathetic nervous system, and that the ability to rapidly shift between these systems is modulated through reflexes of the vagus nerve. Specifically, when the vagus nerve is engaged, this allows the parasympathetic nervous system to maintain visceral homeostasis and lowering heart rate. But when stressors are detected in the environment, this reflex is also able to rapidly suppress and allow the sympathetic nervous system to mobilize the body to respond to stressors. For decades, researchers have worked to capture and characterize the process of physiological regulation to better understand how infants are learning to manage their emotions and what factors may be contributing to optimal or maladaptive patterns of regulation. To measure vagal physiological regulation, we use respiratory sinus rhythmia, or RSA, which measures heart rate variability at the frequency of breathing. And in infant research, tasks like the face-to-face still face have been used to control for aspects of both soothing and stress across enough time to gather average RSA signals. Reliably across these signals, when caregivers are engaging in social play with their baby, we see a group level higher average RSA, reflecting that the infant is in a calm state. But as the caregiver becomes unresponsive and the infant becomes distressed, at the group level we see a lower average RSA, indicating that the infant is in fact suppressing their vagus nerve and increasing their sympathetic nervous response. Finally, as caregivers become responsive again in the soothing reunion phase of the still face task, at the group level we also see a higher RSA, which is characterized as a recovery of vagal tone, where infants are rising again to that visceral homeostasis. I stress average RSA because historically RSA has been limited to aggregate measures that average across epochs 30 seconds or greater due to RSA's slow periodicity and the sampling requirements needed to reliably analyze variability in time series data. Therefore, while we know that overall these values can change significantly across tasks, no prior work has shown the real-time dynamics posited by Porges' polyvagal theory. While many infants do reliably display the RSA reactivity pattern, where RSA is lower during still face phase and higher during the social and reunion phase, not all infants actually show this type of response. Recent meta-analyses have shown that upwards of 50% of infant samples actually do not show this pattern. They may show no changes across tasks in RSA, or conversely, they may show completely opposite patterns where RSA is actually lower during social reunion phases and higher during still face phases. Using a finer time scale, we should be able to understand the nature of these consistencies a little bit better. It could be, for example, that we're not capturing variabilities in actual behavioral responses where infants maybe aren't as distressed as we think they might be, or maybe more distressed, and that these are all averaging out and drawn towards a basic mean. It could also be that infants are engaging in these responses, but at a delayed time period, and that's also being averaged out, being categorized as a non-response. By examining the real-time changes in RSA that are linked to specific behaviors indicating distress, we could reveal more insights into the individual differences and dynamic processes that drive physiological regulation. Another inconsistency to address in the literature is relationships between infant temperament and average RSA changes across tasks. We would expect that temperamental factors associated with regulatory skills like orienting and effort control should map on very well to these RSA differences, but these are actually rare relationships, and most studies report no results. These unanticipated null findings may be a consequence, again, of averaging out effects that may be more sensitive in dynamic real-time measures. And we predict that having a more sensitive measure will be able to delineate these differences between groups. Finally, we not only want to capture RSA reactivity dynamically in real time, but also in everyday context to compare if these responses seen in structured distress tasks are also seen in everyday contexts of distress. Well, tasks like the still phase are really good at controlling noise and confounds in the data and also allowing enough time to actually analyze RSA aggregates. It really limits distress expressions, as many tasks are actually stopped if the infant becomes too distressed. And it also constricts natural soothing interactions in which the mother normally would respond a little bit faster. With advances in wearable technology, we're actually able to capture high-density data in the home covering a large range of distress contexts, really being able to capture what this physiological regulation looked like in everyday atmospheres. Which brings us to the current study. So the data that I'm going to share with you today is leveraging wearable sensors, video data from the home, and caregiver-reported temperament to answer two primary research questions. First, what are the real-time dynamics of RSA around the onset and offset of distress, especially unprompted infant distress, and do they match the theory posited by Porges' polyvagal theory? And do these patterns differ based on individual factors of infant orienting? So how well do the parents believe their caregiver or their infant is regulated? So in this analysis, we included 36 infants that ranged from 1 to 10 months, with an age of around 4.6. We had slightly more females than males, but still about an even split. Exclusion criteria for our study included infants older than 12 months, congenital birth defects or genetic conditions, multiple birth infants, and living greater than 20 miles from our university. We had a decent distribution of race and ethnicity, mostly white, but also representations from white Hispanic, black Hispanic, and multiracial ethnicities. We also had a decent distribution of household income, skewed slightly towards higher annual household incomes. So data on infant distress was annotated from video-recorded intercessions, where we went to the participant's home and set up our sensors as part of a larger study. Our heart rate data was collected via a chest-mounted Mosins Move4 ECG sensor that collects at 1,024 hertz. It's very comfortably on the baby's chest. They are able to do everything they want while wearing it. Our factor of infant temperament was derived from the infant behavior questionnaire, the revised very short form, really looking at typical behaviors in the baby oriented towards or away, towards soothing stimuli or away from distressing. So how well are they able to regulate on their own based on caregiver reports? And overall, the session was pretty unstructured. We completed about 10 minutes of structured activities like free play and reactivity, but most of the time it was just walking around the home and capturing just natural instances of infant distress. To annotate our infant distress, we have reliable human coders, our wonderful RAs, annotate all instances of both fussing and crying that lasted greater than 5 seconds from our inter-session recordings using Manifold. And overall, we had 141 total distress events included in this analysis that had both useful ECG data and were greater than 5 seconds. The range in total was up to 118 seconds, but a majority of the data fell at 33 seconds and below, so that's what was included in our distress analyses. And infants on average had about 4 distress episodes ranging from 1 to 13 per session. So we definitely got some crying in there. All right, now the very exciting part, calculating dynamic RSA. So using recent published and validated methods by Drew Abney and colleagues, we calculated continuous RSA with a 15-second sliding window, updating the mean every 200 milliseconds. So we had a RSA data at 5 hertz. And so we calculated this for all RSA, or all crying segments. So RSA was extracted and time-locked around the onset and offset of distress. And what we wanted to see was how does RSA change relative to just before the onset of an event. So we time-locked and then subtracted those RSA values within the event from the RSA value directly prior to it to see how does RSA change relative to time that it actually occurred in. Then to see how these changes might be different from chance and is this a significant reduction or not, we actually used a bootstrapping method to calculate confidence intervals, doing a shuffling of all of our RSA data with 1,000 iterations. Okay, all the results. Okay, our first hypothesis was that in accordance with Porges' polyvagal theory, the onset of distress should be accompanied by a relative significant decrease in RSA, indicating that as infants are displaying distress, we should see a rapid decline, as you see in the right, in RSA levels, showing the suppression of the vagus nerve. And we do. This is across all infants in our sample, the average RSA change that was relative. And what we find is, if we look at this gray ribbon across, that's our 95% confidence interval, saying what's the chance change in RSA. At around 13.4 seconds, that change goes significantly below chance, and we see that there is a significant reduction in RSA, supporting our first hypothesis. So infants do suppress the vagus nerve when they're crying, even in naturalistic context. Our second hypothesis was about vagal recovery. So the onset of distress should be accompanied by a relative significant increase in RSA, showing that as infants are naturally being soothed or regulating themselves, they should have a recovery of vagal tone, shown by that sharp increase in RSA that's significantly different from chance. And this time we looked at the whole minute after the offset of distress across our infants. And while it took a little while, we did see a significant increase in RSA that was completely different from chance at about 28 seconds to almost 50, saying that infants did in fact recover from that vagal suppression to recover vagal tone and try to get back to visceral homeostasis. So our hypothesis 2 is also supported. There are real-time dynamic changes, but not upwards until 28 seconds after the offset of distress across our infants. All right, now our group level hypotheses. So in line with the idea that beta regulators should have better physiological regulation, we hypothesized that infants rated as high in orienting would have a more significant reduction in RSA after distress onset than infants low in orienting. To complete this analysis, we did a median split of our orienting scores to create a high and low orienting group. These do not differ based on age or gender. And what we found is that those group level effects we just observed in the group level analysis are actually completely driven by infants who are rated higher in orienting. So the blue line is those infants rated higher in orienting, and the yellow is those rated as poorer regulators by their parents. And they actually had no significant withdrawal of the vagal brake during distress, and they actually had a significant increase in RSA across this task. So really unexpected. So hypothesis 3 is also supported. There are significant differences, and there are infants who are leading these group level patterns based on temperamental differences. Finally, we also hypothesize that infants with higher orienting will have a more significant increase in RSA following distress resolution than infants low in orienting, just showing that they're really able to recover their vagal tone after distress offset. And what we found is that actually both groups, regardless of the suppression of the vagal brake seen during stress, they both had a recovery of the vagal tone following distress offset. But infants rated higher in orienting did have a more sustained and higher amplitude in this significant increase in RSA after distress. So really, again, showing that while it might be delayed, it's a stronger response. And these are, again, pointing to individual differences in dynamic RSA. So our final hypothesis was also significant. Let's wrap up all those beautiful graphs. So first, we have shown that RSA does dynamically decrease following distress onset and recovers following stress offset at the group level. Our results provide the first empirical evidence confirming Porges' polyvagal theory, both in real time and in unprompted, unstructured infant distress events. Based on our results, the response patterns proposed by Porges' theory, especially in vagal suppression during distress, appear to best capture those infants who are rated as better regulators by their caregivers and not those who are rated as poor regulators, just indicating the importance of controlling for individual factors of temperament when looking at RSA responses, and hopefully prompting even more work into looking at infant temperament and dynamic RSA. All right, I'd like to thank my team, my advisor, the grad students, and my amazing research assistants in the lab, and I would like to thank you all for your attention.
So we have a couple of minutes for questions if anyone wants to ask questions specifically for Anna, and we'll start setting up the next talk.